If you guys remember, back in October, it seems like forever ago, Fred Zelt was gracious enough to tell us about Fallingwater. And it was such a great talk. And when he ended during Q&A, he goes, well, I have a lot more I can say. We're like, well, you got to come back. Yeah. And I heard from many of you, like, yeah, let's bring Fred back. So it's not an encore because this is all new material, but it's a building on last fall's talk. And so I'm going to forego the introductions and just say, well, you guys remember October? Well, Fred's back. So here you go. I'm going to turn it over to you.
Okay, thanks, Al.
Here you go.
Let me know when I'm 15. Thanks. And thanks for a chance to come back. I'll cover some aspects of Fallingwater we didn't get to in October, but I'm going to show you materials I've never shown publicly before. And having this reason to put materials together was a fun learning experience for me. We're going to talk about these 4 great Frank Lloyd Wright houses in chronological order, starting with Taliesin, going to Graycliff, then Fallingwater, and Kentuck Knob. Well, I had 2 acknowledgement slides in October for Fallingwater, and there were people in the room here who contributed to that, many of you actually. So these are the additional acknowledgements. The folks, Ryan Hewson has hosted me at Taliesin. The folks of the Frank Lloyd Wright Foundation, Taliesin Preservation Institute were just great. At Graycliff, Ryan Gravel has been great, the Graycliff Conservancy. Folks at Penn-Dixie Fossil Park, too. And then Kentuck Knob, Tim Fisher, and the docents there. You'll see a contribution from Jim Shawless there as well. So lots of help with these. So those aren't the only 4 stone buildings Frank Lloyd Wright built. The first of the 4 I'll show you, Taliesin, started in 1911. It was really a test bed for organic architecture concepts for Wright. And he modified it, changed it, added to it, rebuilt it through the rest of his life until he passed in 1959. So it was a stone test bed. But he did build some stone buildings before that, including Hillside on the same grounds as Taliesin. But there are other buildings with stone components during the Prairie phase, although by far most buildings he built, residences he built in the Prairie phase and in the organic architecture before and after Taliesin, by far most were wood or brick. But during the organic architecture phase, starting with Graycliff, the first building he built for a client in North America with significant stone components and the organic design concepts he had developed at Taliesin. So starting with Graycliff, I count at least 33 stone houses that he built just during that phase. But there are many more that are brick and wood, and they're beautiful. But I'm a geologist. I'm going to try and stay in my lane, and we're going to focus on the ones with a lot of geology, including those 4. Notice he even had a stint in Japan where he used a vesicular tuff as a feature stone. It's not really an organic design in my mind because the stone finishes were smooth finishes or they were highly geometric stylized design, not just boulders or split open faces. So we're going to focus on those 4, talk about them in order. I've already talked about Prairie School and organic design, and we might not all be on the same page there. So I'll just use these windows to illustrate the concept of these different phases of his career. He really reinvented himself. A lot of people know Wright buildings as the Prairie School buildings, that beautiful oak furniture. You can see the highly stylized window in the Roby house here. See the diamond shapes in it. So highly stylized, beautiful designs in the Prairie School, highly finished interiors. A lot of times if there was stonework, the stone might be a finished stone, even with lettering carved in it. Graycliff, as I mentioned, was a transition. It's got a lot of Prairie School lines, but it has a lot of design features that he used at Taliesin or built into Graycliff as well. It's a transition. And then after that, Fallingwater was his masterpiece of organic architecture. We'll talk a little bit more about that one. A lot of design features from Taliesin built into that. And then Kentuck Knob was a Grand Usonian house built late in his career in the 1950s. And look at the windows. Graycliff, it's a picture window. You can see the main natural feature. You don't have artwork in the window in the way. You can see the lake, the main natural feature there. but there's a picture frame around it still. It's stylized a little bit. And then see it Fallingwater. It's a mitered glass corner window. You can't really tell there's a window there. You can see the frame for it, but it's really blurring the boundary between inside and outside and bringing that nature inside. And then look at Kentuck Knob. There's not even a frame. The glass is set into the stone. When you stand in the living room and look at this window, look through the window, you can't even tell there's a window there. So you can see his transition then between, I think, prairie design and organic architecture. So we'll start with Taliesin. It's built into a hillside in Wisconsin. You can see the stonework there. There's stucco that used sand from the nearby Wisconsin River. This geologic map, you can see the bedrock around Taliesin is Cambrian Ordovician age. And you see the white dashed line, that's the glacial limit, Pleistocene glacial limit, and it's inside the driftless area. Does anybody not know what the driftless area is? Glaciers went around it. You can picture the lakes, the troughs where the lakes are today, help shunting the glaciers away from that area, and the Wisconsin Dome Precambrian rocks also being sort of an anvil. So it was never glaciated during the Pleistocene. And I'll mention that when you see, I'll show you landscapes here in the driftless. When you see those landscapes, think about this part of Pennsylvania that really has similar geology, surrounded on three sides by glaciers, streams that used to flow north that became proglacial lakes, flat-floored valleys with steep hill slopes because they were never glaciated. To me, after having seen the driftless here, this is Pennsylvania's driftless area. It's really similar topography, different age rocks, but similar. So there's a look at the shaded relief map, a little closer look. You can see Taliesin there with the star. Notice the flat-floored Wisconsin River just north of it. The Wisconsin River there is thought actually before glacial times and early in the Pleistocene to have flowed from west to east. And then eventually during the Pleistocene at some point, glaciers came, stopped that flow, it became a proglacial lake, spilled over, and it joins the Mississippi and they both flow south now. So it has that aspect to the story. And you can see the flat floodplain. As I mentioned, there was a proglacial lake here at some point. And look at the flat-floored valleys of the tributaries, including the Jones Valley that runs past Taliesin. And you'll see pictures of the landscape, but you could see maps in that driftless area of Pennsylvania that look pretty similar in terms of the topography, I think. There's the geology. It's older bedrock than that part of Pennsylvania, though. There are Cambrian sandstones in the earth tones. You can see the pinks are the Pleistocene and more recent Quaternary sediments. And then the blue is Ordovician carbonates. The carbonates hold up the high ground here. The ridge tops are typically carbonates, Ordovician carbonates. The Cambrian sandstones are not as cemented as sandstones we're used to in Pennsylvania. There's work done a little farther south in Wisconsin with algal organic marine matter in Ordovician rocks. And they estimated the maximum burial depth, the thermal maturity there suggested only 700 meters. And if you add a little more section going down to the Cambrian, I think the Cambrian sandstones here were only ever buried about 3,000 feet. And they're 490 million years old. So they're not super well cemented. Some are more cemented than others. So you'll see low Cambrian sandstone hills, and then the higher hills are capped with that Ordovician, mostly dolomites, Ordovician carbonates. To clue into a little geologic cross-section, we're going to focus on the St. Lawrence Formation here. These are Cambrian rocks, Ordovician rocks above this line. You see those Ordovician carbonates. And in the Cambrian, there's some sandstones or shoreline sandstones that were used in other buildings on the Taliesin grounds that we won't talk about. But the Taliesin building itself is made of St. Lawrence Formation, which is a mix of carbonates. You see offshore carbonates here. They're now dolomitized, and sands coming from the shoreline. So it's a mix of, it's a sandy dolomite, dolomitic sandstones. See the staple shapes? There were microbial buildups in the Cambrian, and that's what that's meant to reflect. And I think I'm going to try to show you what I think is some microbial laminations in the rocks in Taliesin and in a quarry as well. So we'll take a little closer view of the area. There's a satellite image. You can see the flat-floored Jones Valley, agricultural croplands valley. There's the Wisconsin River. And the red arrows indicate the next series of slides We're just going to show you the driftless terrain here from north to south. We're going to start up here at Phoebe Point, a favorite viewpoint of Wright's. He sometimes took visitors there if you were lucky. There's a trail the Taliesin folks own now, that land that you can go visit. So we'll look from there and we'll work our way south toward the Midway Hill, one of these low Cambrian sandstone hills. Midway Hill and Barn will be the last of those four. So here we are looking east. You see the Wisconsin River Valley, the hill capped with Ordovician carbonates in the distance there, and the flat-floored Jones Valley in between. Looking to the southeast from Phoebe Point, you see the Jones Valley, you see those moderate hill slopes with carbonates holding up the crests, and in the mid-ground here are Cambrian sandstone lower hills, and this is Taliesin in the trees. It's on this hill slope. It's not at the crest of those hills. It's built into that hill slope, a favorite viewpoint of Wright's at Phoebe Point. Here we are at Taliesin itself, a view to the southwest toward some of these Cambrian sandstone intermediate height hills. Notice Wright called these stickouts. See how some of the stones extend from the mortar a little farther? He built some stone buildings before Taliesin, as we saw, but this was the first building where he used those stickouts. Those are a common feature of organic design in other stone houses after Graycliff, including at Fallingwater. So there's the last of these. We're standing on one of those sandstone hills partway up, looking past the Midway Barn. There's the flat-floored Jones Valley and the moderate hill slopes in this driftless terrain. If we look at a shaded relief map, you can see those four viewpoints that we just saw. And I'm going to show you a cross-section in a couple slides that goes from north here to south. It starts with the Wisconsin River, climbs up this hill to Ordovician carbonates. It goes down to the Jones Valley, climbs back on this hill behind Taliesin, one of these Cambrian sandstone hills. You see Taliesin is not at the crest. It's built into the hillside. That's part of the natural theme here, not putting it as a beacon right on top, but it's kind of built into the hill. We'll go down to the Jones Valley and the pond, and then we'll come up to this erosional remnant of Cambrian sandstone at Midway Hill, and then we'll head almost straight south past a sandstone quarry in that Jordan formation, and then back down into Jones Valley. You see the buildings here, the shapes of them. There's Taliesin itself. That's the building we're going to talk about. I'm not going to talk about hillside. It has sandstones as well as dolomitic sandstones, some sandstones from this quarry. I've put together a longer talk about Taliesin. That's the way I built this talk. I made like a 100-slide talk about Taliesin, about all the outcrops I studied there, paleocurrents and quarries, both quarries and all the buildings. And then I pared it down for this. So my intention is to record that talk. It'll probably be an hour-long talk about Taliesin geology. And when the Taliesin folks and I are satisfied with it, I'll send a link to Al. So if you want to sit down with a beverage sometime and learn more about the other parts of Taliesin, it'll exist. So here we go. We're going to head toward a cross-section. First, a geologic map, a close-up. The river here in the blue and the pond, but the other blues are those Ordovician carbonates that cap the hills I mentioned because they're resistant to erosion. These earth tones, green and brown, those are Cambrian sandstones. And there's Phoebe Point Quarry. So Phoebe Point was here. The quarry nearby, Phoebe Point Quarry, it's that St. Lawrence formation that you saw in the cross-section, a mix of dolomite and sand. And we'll look at Phoebe Point Quarry, and we'll look at Taliesin. There's the cross-section. You see it goes from the river in the north, up on top of that hill with Ordovician carbonates on top, past the Phoebe Point Quarry that we'll see, and Phoebe Point that we already saw, then down into these Cambrian sandstones, up onto the hill behind Taliesin, past Taliesin, down to the pond at the edge of the Jones Valley, over this erosional remnant of Midway Hill with Cambrian sandstones, past a Jordan Formation sandstone quarry that probably supplied stone to hillside as part of hillside, and then back down toward the valley. And if you're sharp-eyed, as I know you all are, as geoscientists, you'll have maybe seen that there's a little bit of dip to the south, and that's the regional dip, with, remember, Precambrian exposed to the north, and there are younger Paleozoic rocks exposed to the south. So you can even see a little bit of the dip, regional dip in the cross-section. So here's a first view of Phoebe Point quarry. You see the rock hammer circled for scale. These quarries are overgrown. They haven't been used in quite a while. Here's a close-up view of some of the stone in the quarry. It's got this mottled texture. So it's undergone dolomitization, and then there's a weathering rind. See this chip of rock? See how it's a different color inside with a more oxidized outside, this golden brown iron oxide color. Of course, there's iron along with magnesium in dolomites typically. So I can tell you, having hit this rock with a hammer in the quarry, the rind is not as hard as the core. And this sample is sitting on the table here. There's stone from each of these houses that we talk about on the table. So there's a weathering rind here too. So it's dolomitized, then there's a weathering rind. It's notorious that you can see sedimentary structures better in core than you can in outcrops in this rock. And in core, you can see flat burrows, and you can see a clotted texture. Anybody know what Cambrian clotted texture would be called? With microbial light and sediment together? Thrombolytic texture. Thrombosis, right? Clot. So thrombolytic texture. There's modeling from that, and there's modeling from horizontal burrows too. But it's hard to pick that out in a lot of the outcrops. You can see it better in cores from what people have written. With the sunlight on the bedding plane here, I hope you can see some traces of horizontal burrows in this slab from the quarry. So you can see them sometimes, but they're kind of cryptic. Here's another view that's a 2-meter tall Jacob staff there in white. You see some slabby beds at the top. So the pavers at Taliesin came from this stone too. And it would be easy to harvest those as pavers because of the right thickness, but they have a lot of that weathered rind to them that's not so hard. So it's been tough for the preservationists as they've had to regrout the pavers. They've a lot of times just can't preserve it as an unbroken piece. So some of the pavers at Taliesin now are replacement carbonates. They're not the original, but we'll see original ones too. And all the ones inside, as far as I can tell, are original St. Lawrence Formation. You see there's some thicker bedding, some medium scale bedding too here in the quarry. Here's a look at another face. See the mottled texture, but you can see a little bit of lamination. We're going to look more closely at those two boxes. Notice the flaty beds above that would be natural to use for pavers as well. So here's a closer look inside those two boxes. I hope you can see there is some lamination here. Maybe it's a microbial mat lamination. I'm not going to be too definitive about that with this, but maybe it is. A lot of this mottled texture that could be the thrombolytic or horizontal burrows or both combined. But the box at the bottom, I think there are definitely some clear burrows in that one. So sometimes you can see the sedimentary structures clearly, but it's tough to see them in these natural exposures. This is also in the quarry, and you'll see that in the upper left there's a joint here that's open, and dolomite dissolves too, right? And there's been freeze-thaw cycles here as well, even though it wasn't glaciated. So there's an open joint there, open fracture, and on the natural rock face here, there are essentially cave deposits. This is white calcite. So it's a limestone deposit. See the bumpy nature of it? And this piece on the right is a piece of that. That's on the table over there. You can see this white crust on joint surfaces in places, and sometimes they're on bedding plane surfaces also in the quarry. And then I noticed the life here. This is a fern. It's a smooth cliff break, a fern that loves limestones. And none of them were growing on dolomite. They're all growing on the limestone crust. Isn't that cool? So I loved seeing that. And then when I went back to Taliesin after the quarry, I saw this. So here's Taliesin with this dolomitic sandstone built into the walls. These are replacement pavers. It would originally have been, this is pavers. There are original pavers in this courtyard area too, but look at this. It's growing out of the mortar that's more calcic than the dolomitic sandstone. And that's a known thing with cliff break. I've read a report in upstate New York where they grow on walls out of the mortar in the wall as opposed to the stone. So I thought that was a really neat, horticultural tie between nature and natural outcrop and here at Taliesin. This is the courtyard area too. There's a chimney mass here. See all those stickouts? And in the late afternoon sun, see the golden brown color of that? we'll talk about that a little bit later. For Kentuck Knob, the client, Edgar Kaufman, went to Taliesin early in the design phase, or not Kentuck Knob. For Fallingwater, Edgar Kaufman went to Taliesin early in the design phase for Fallingwater. It's a famous story. He showed up with little warning. And he saw these organic design features that were built into Taliesin, and many of them are built into Fallingwater. So he understood use of stickouts and many other features. The clients for Kentuck Knob, the Hagens, also visited Taliesin when Kentuck Knob was in the design stages. And they also saw these design features. Remember this golden brown color when we talk about the stone at Kentuck Knob, which is a different lithology, but it's the same color. So remember that they saw this before they decided on a building stone for Kentuck Knob. We'll take a closer look here. You see these stickouts, and look, there's that white crust. So this is an organic design feature. I think they preferentially showed these crusts, made them visible to people. There are mineralized joints on display at Fallingwater. There are mineralized joints on display at Kentuck Knob, other houses too. There are fossils on display at Graycliff, mineralized joints on display there too. So they made an effort to show these organic design features that are also geologic features. Here's the living room inside. Notice the same stone. See, there are stickouts inside, not just outside. And see how they've tipped up a slab here so that you're seeing the geologic texture of the rock as sort of an art object above the living room fireplace. These are the same stone, but they're coated with, in this case, I think shellac, so they're a different color. But it's the same stone like we talked about before as pavers. There's a closer view. Maybe you can see a little bit of trace of horizontal burrowing in this, but it's tough. It's definitely a clotted sort of irregular fabric, though. There are many fireplaces built into Taliesin. I'm not going to show you all of them. I'm going to show you a couple more, though. This is Mr. Wright's bedroom. You see the irregular shapes of the pavers here? That's another organic design element. The cheapest thing to do would be to cut them into rectangles or squares and just lay them out quickly. But these are individually pieced like a jigsaw puzzle. And that's an organic design feature that's common to other stone Wright houses at Graycliff and beyond. You see the stickouts. You'll notice a red stone here. I'll talk about those a little bit later too. And look at this stone on the top where bedding is on display. There's another closer view of it. You can see the pavers too, the irregular shapes. And then here's a view from the side. So it's got a bit of this clotted texture, maybe a combination of burrowing and thrombolytic texture. It's kind of hard to differentiate them in that view. A lot of the lighting at Taliesin and other buildings Wright designed is indirect lighting. It's kind of hard to see sedimentary features with indirect lighting. So this is a room where there was a lamp. And so we're going to look at the same kind of bedding plane here. That's what I'm going to come around to. But this is the gold room. This is a room that when he was apprentice, John Lautner, the famous California architect later on, stayed in this room as an apprentice. There's an apprenticeship program. See the stickouts in the rough stone wall? See how it's not finished stone, it's split stone, part of the organic design. There's the fireplace. There's another one of these red stones. It's a red patina. It's an iron oxide patina. You know, we talked about that dolomites often have a little bit of iron in them. There were two major fires at Taliesin and some minor ones too. And in the rebuilding and in extensions later on, sometimes stones that were baked by those fires were built into walls in Taliesin and preserved that way. I've stalled long enough. I hope that you can see vugs. So vugs are another common feature of the dolomitic sandstone in the St. Lawrence Formation. And there you see them in the bedding plane, nice vugs. And with the light from the side, I hope you can see these traces that I think are likely horizontal burrowing. So you can see at least a bit of that in the stone here. This is the loggia area. You'll notice the pavers with irregular outlines down here, these coated pavers. But look at this. We'll take a closer look at that. And you can see a lot of blocks of stone here that have been baked in one or more of the fires and then rebuilt into walls. And those are kind of scattered around. So that's another feature of Taliesin. So that's been geologic highlights of Taliesin itself. One thing I didn't mention is that the Stucco here incorporates sand that came from the Wisconsin River. Wright wrote about that in other places too, the natural sources of sand in the stucco as part of it, in his mind, part of the organic design. Maybe you, like I do, maybe you know an artist who does things like that, incorporates sand in paint to have part of the place present. We'll move on to Graycliff now. It has a water feature in front, another common design feature. You saw the pond at Taliesin on the maps. You can see the main natural feature of the site through the house, through the living room, in the center of the house, and through the dining room over here. All this stone with some iron oxide patina. We'll talk a lot about the stone. The stucco here includes sand from the beach. Wright wrote about that too, just like the river sand use. And here we are in the Devonian outcrop belt in western New York on the shoreline of Lake Erie within the area that's been glaciated. So the landscape, the bedrock would have glacial erratics sitting on top of it. It's actually a complex of 3 structures. Each of them has similar stone walls, and they have stone pavers like the ones we'll see too. We're really going to focus on the main house or the estate house. Nice view of the lake. See through the house here. Remember that dining room window I showed you for Graycliff? Well, there it is, with that little bit of picture frame left. And we haven't totally transitioned away from that design element. Okay, thanks. And the stone here, notice how this recessed light is canted at 45 degrees. There's a diamond-shaped theme that actually has a link to geology here. So see how it fits with a diamond theme, having the light turned. We'll see other examples of the diamond theme. Look how the house parallels the lakeshore and the cliff. So part of organic design was siting these houses in with the terrain. And in map view, you can see that. The house also is sited. This is the boundary of the property. So it fits perfectly the boundary of the property, but it also fits the lakeshore trend. And later, Wright wrote that this was an ideal azimuth for organic design houses because for much of the year, in morning, midday, or afternoon, the sun would reach every side of the house for much of the year. So 50 to 70 degree azimuth, he wrote, was ideal for these buildings, and this one happens to be right in the middle at 60. But it also fits the property boundaries, and it also fits the lake. It fits all of those. Tichenor limestone blocks on the beach here were harvested along with glacial erratics. This was the base of a cliff tower or a stair tower that enabled people to go down steps to the beach. The cliff here is eroded back about 15 feet in 90 or 100 years since Graycliff was built. So there's no more tower. It became non-functional. The Tichenor limestone is about 1.5 feet thick. It's a condensed section. It's a skeletal grainstone or packstone. It's full of fossils, disarticulated crinoid column pieces. Grabeau in 1899 published fauna on 18 Mile Creek, which is just around the corner next to here, a classic study in these shales in the Tichenor. And this Middle Devonian marine unit had 59 taxa of macrofossils, marine macrofossils. And you'll see some examples. That's what's built into the walls. So there are hundreds of those fossils on display at Graycliff. Notice the patina here. In places, the limestone has pyrite on the base, in other places on the top, some places both. And sometimes that's made a patina like you have now on the exterior walls of Graycliff. So condensed section, it's a marker bed. It's been traced for more than 100 miles east of here. These beds, like this is a named marker bed, this is a named marker bed, this is a named marker bed that have been traced tens to 100 miles. The stratigraphy here is highly refined along with the paleontology. Tichenor limestone is a part of that. And I should mention that the Tichenor, the shale above it, and the shale immediately below are exposed in an old quarry that's now Penn-Dixie Fossil Park, only about 10 miles from here. So you can walk on the Tichenor limestone, look at it, you can collect fossils from it and from the shales above and below in Penn-Dixie Fossil Park. And in the summertime, they collaborate, Graycliff and Penn-Dixie, and you can do a Wright Rocks tour and tour the house, go down on the beach, and then have a ticket to go to Penn-Dixie and collect fossils from the same rocks that you see. It's really a neat geologic and architectural experience. Here we're looking up at the bottom of that ledge of Tishner limestone. Look at the natural fractures. See how there's a 60-degree angle here between north-south and northwest-southeast fractures. You get various shapes of boulders on the beach, but some of them are this rhomboidal or flattened diamond shape. You see a notebook for scale there. And also notice the weathered pyrite patina. Well, this is the diamond window in a really prominent spot. You can see inside and outside views of the diamond window. This isn't the first diamond window Wright ever built. You saw a diamond shape in the Roby house, the leaded glass there in the Prairie style house. He built a school in Japan that had a big diamond window. It matches the roof line, that kind of 60-degree angle if you have 30-degree slope on the roof. So he used that other places. But here, look at the boulder. It matched nature in this case. And so there's a diamond theme for the house, and that's the diamond window. Look at the patio. Look how the pavers there are tilted 45 degrees. This is the back patio. See how that fits the diamond theme too? And look at these pavements of Tishner limestone, about 1.5 miles from Graycliff, southwest. The regional dip brings them down to the beach, and you can walk on top, see the natural fractures, and see how the natural fractures make a diamond shape here, make a diamond shape there. And look at the comparison between nature and these pavers. Now, these pavers aren't Tishner limestone. Those are fine-grained sandstones. They're Medina Silurian sandstones, probably quarried along the Erie Canal and transported to Buffalo and built into sidewalks. In the 1920s, they were replacing stone sidewalks with concrete and cement, so these are recycled pavers from Buffalo and Silurian sandstone. I put some effort into trying to understand the natural fractures. These are the fractures here. These are the fractures at the other outcrop 1.5 miles away, a place I call Flexure Cove. And these are the main fracture sets, I think, that set up boulders like this at Graycliff. This, you'll recognize, this northwest-southeast orientation. It looks like it's a cross-strike orientation for Alleghanian deformation. I think these were formed deep at maximum burial and around Alleghanian deformation time. There's another north-south orientation that's important here. There's a third orientation commonly too. It's not as well represented here because it was hard to identify it clearly from the beach. But you could identify all of the fractures really clearly here. So all the fractures are identified well on those. So I put some effort into thinking about fractures. This is a compilation of other people's work with some of my fracture orientations too. And you'll all know that these surface anticlines, dashed lines, the big surface anticlines are where there's halite facies in the saline salt. That's been known for a long time. And you can see Engelder and Geisser's cross-strike fractures, and see how this lines up with that. That's one of those, this is where Graycliff is. That's one of those fracture orientations. The north-south orientation, Lash and Engelder wrote about that too. They suggested that maybe that's an earlier phase of Alleghanian tectonism that relates to. There are other ideas about that. Jacoby and others have written about north-south basement faults that were active through time here. There are a couple different reasons why that could be. But I think these are deep-formed structures or deep-formed joints. These are generalized joints in the Devonian shales. I'm going to show you some detail from this box that's near Graycliff. And I'm going to show you Riley Beach here. Riley Beach is almost in Pennsylvania, so we're almost there. Those are a couple places I'll zoom in on. When I was looking at those fractures and reading about things, I came across this. It's in your library from 1843. It's by Hall, and he saw these compressional structures, thrust faults and folds. This is at Riley, almost in Pennsylvania. This is not super far from Graycliff. That's the place I call Flexure Cove. And some of them are in stream bottoms. People have studied those, but nobody had studied these ones on the lakeshore since the 1800s. I found about a dozen of them. I'm going to show you a few of them. They're really pretty neat structures. So here's Ripley Beach. It's a public beach. There are steps in the summertime, just 10 meters away from this, 2 meters for scale. I think this is a post-glacial pop-up. And there's a historic nature to this too. G.K. Gilbert had looked at these little surface ridges in northern New York, glaciated area, northern Ohio, wondered whether those were tectonic or what. You can't see cross sections for them though. And he came to this structure from Hall from 1843, and the structure went away with depth. There was no structure. He decided it had to be a shallow form structure. And I think you can see that the structure goes away at depth. When you go lateral to it, there's no sign of it. There's no sign of a detachment. See how the amount of shortening increases a lot upward? The style of it increases too. See, the bottom detachment has some gouge in it, but this detachment has a tent-shaped fold or an A fold above it that looks like it has an open hinge, as though it had to be really shallow because it's just open there. So I think there's good evidence that this is also a post-glacial pop-up structure. And like I said, I've seen about a dozen of these now. Another one that Hall wrote about and was mentioned also by Grabeau in 1898, but not since then, was a place where the top of the Tichenor is about 4 feet displaced here. In the 1800s, they described there being a thrust fault here. Today it's covered, so I can't tell you that there's a thrust fault there. But look at the arrangement of these thrust faults with opposing divergences in the upper Devonian shales above this. This is this place I mentioned where we looked at the pavement with the joints at Flexer Cove, 1.5 miles from Graycliff. We're going to take a closer look at those. You'll see that in an end-on view with a hammer for scale, see there's a fold below that middle fault. There's a fold above the middle fault. Here with foreshortening and the hammer in the same position, see that fold. So this is one of a dozen of these kinds of structures. I'll show you a couple more here, but this is a summary of Devonian shale joints that I measured with these colored lines. But then the red lines and the brown, those are folds. The brown are folds, and the red lines are the direction of compression implied by those folds, or here you can see the symbol for a fault. And when you plot those on a map, the red lines and the black arrows indicate the compression of these small structures. This is the first one I measured. I thought, okay, that's an Alleghanian compressional fold. And then I measured this one. Well, that's not an Alleghanian orientation. And then I measured those, and there's a consistent and progressive rotation in these little pop-up structures through here. So why is that? Well, there are a lot of reasons that could be. One idea is, with an analogy of the floor of Lake Ontario, there are great pop-up structures on the floor of Lake Ontario that are post-glacial. They go for miles, and they're clear on the bathymetry, and the ages have been studied because there's sediment on top of them, lake sediment on top. And the first ones are parallel to the retreating ice front. So as the ice retreats, there's a bulge in front of it, and as the ice retreats, that bulge retreats too, and the state of stress changes in the rocks as it retreats. The older pop-ups have variable orientations because the state of stress had changed. So that's one of the many possibilities for why these have this arrangement of different orientations. But I think it's clear that they're post-glacial pop-ups. These helped convince me of that too. These are from Point Breeze Beach, another public beach, the one that's to the southwest there. See how those are tent-shaped folds or A folds? This one has an open and irregular axial fracture. Here's a little thrust fault with a fold that's open inside. Those have to be shallow structures, I think probably post-glacial. And here is another structure at a place called Faults Cove with those stacked thrust faults. See the limestone layer here? It's a marker. There's no vertical displacement between the hanging wall and footwall of this. It's not that kind of structure. It's a vertical pop-up structure. When you go away from it, there's just no structure. You don't see any detachment. And the hanging wall and footwall, when you go away from it, there's no vertical offset. It's just a shallow structure. So we'll go back to the house then at Graycliff. You can see these stone walls. There's a lot of Tichenor limestone built into them. Look at this horn coral that's just stuck in the mortar right near the front door, an organic design feature. When we look this way toward the water feature, See that? You recognize that shape? It's rounded a bit from being on the beach and just stuck right by the front door there. There are hundreds of macrofossils, these Middle Devonian fossils. Most of the wallstone is Tichenor limestone. There are horn corals, colonial corals, brachiopods. These were pyritized ones that are weathered. There's bryozoans, lots of different kinds of fossils. Grabeau found 59 taxo fossils in that rock unit. This is the heart of the house for Wright, was the living room fireplace. Notice there's a concentration of glacial erratics. There are gneisses and granites that were split and put into these walls too. And there's a special concentration of them here. Maybe they were to reflect firelight on those split crystalline surfaces. And look, there's a brachiopod just stuck right in the mortar in this heart of the house. Here you can see during construction and now see the patina from the weathered pyrite, just like on the beach. Another feature here. And this is a favorite back corner room. You can see these design elements. See the diamond orientation of the recessed light. See the stone. You can even pick out a fossil from here in the stone boulders. And see the stone floors, the pavers with lots of different shapes, like we saw at Taliesin. Okay, now we're going to move to Kentuck Knob and Fallingwater, down in Pennsylvanian rocks in southwestern Pennsylvania, never glaciated. We talked a lot about the stone. I'm really not going to dwell on that. Just to remind you of the setting, we're sitting in the Ligonier syncline in between the Alleghanian folds of Chestnut Ridge and the Laurel Hill anticline in the Laurel Highlands. Jim's geologic map, the house here sits on Homewood sandstone, of course, to medium grain fluvial sandstone, bedrock cliff forming, and the house stone comes from this quarry in the uppermost part of the Pottsville, a more bedded unit, tidal flats or beach, fine grained to very fine grained sandstones, lots of trace fossils, ripple marks. This is what the rocks look like. There's the Homewood with fluvial channels in it, and you see the bedded Fallingwater sandstone at the top of the outcrop. So what we didn't talk about in October was why the house is oriented as it is. It's within that range that Wright liked. It's at 53 degrees, between 50 and 70 degrees azimuth, and it fits Bear Run. It's cantilevered over Bear Run and over the upper waterfall. And what's the geologic origin of that orientation of this reach of Bear Run? Well, I think you can probably guess that. It's along the Alleghanian tectonic grain. So here's literally a textbook view of fractures in a stiff folded layer. I'll show orthogonal fracture set in blue and oblique fractures, which I'll call conjugate fractures, in red. And I want to show you a really nice example from Bachman Rock Overlook in Ohio State Park, and then we'll go back to Fallingwater. So here's Bachman Rock Overlook. A lot of you have seen this. This is Homewood sandstone. See the sort of cubic arrangement of the outcrop here from those orthogonal fractures. They happen at smaller scales too. The pencils here and the arrows all point north, and this is oriented to those. So those are the blue fractures here from Bachman Rock. And there are beautiful conjugate fractures. See those conjugate fractures? And those are shown in red here. So the orientations of the conjugate fractures change within this area, and that would be a great geologic study, but I hope you're convinced that they both do exist here, at least at Bachman Rock. Now we're going to look at an outcrop along Bear Run away from the house, and when floodwaters scour away leaves and a lot of the moss, there's that fold parallel 40-degree azimuth, and you see the cross-fold orientation, and look at these beautiful conjugate fractures here. So you have both fracture sets here. Now next we're going to take a look from the bridge toward this part of Fallingwater. We're going to look down this reach of Bear Run, and you know that that reach is at 40 degrees, right? It fits that Alleghanian azimuth. So here we're looking at from the bridge, the house cantilevered over the bridge and the upper waterfall, and the house and the waterfall, or the house and this reach of Bear Run are parallel. You can see the house orientation in the shadow of the house too. Looking down from the patio, so now we're where this person is standing, looking down onto the bedrock. There's the fold parallel fracture orientation that forms this orientation of this reach of Bear Run, and also is parallel to the house. And there's the cross-fold orientation. Those are the main fracture sets here. The waterfall's east-west. It's neither of those orientations. When I plotted this up, I thought, well, shouldn't the waterfall be a fracture orientation? But it's in between them. Ohio Falls does the same thing, orthogonal fractures, and it's east-west. Niagara Falls, American Falls does the same thing, orthogonal fractures. The trend of the lip of the waterfall is oblique to that. So some waterfalls, the way they migrate up dip, have this kind of oblique orientation. There's a view straight down. You can see the fractures measured. You see the same kind of plot for those. The orthogonal ones are dominant. Notice the notches. And it's common for there to be notches that are fractures, but sometimes the overall trend of the waterfall is oblique to any of the major fractures. Now we're going to look from the upper waterfall downstream to the lower waterfall here. Measured fractures in this too, and they're dominated by the conjugate fracture set, and this waterfall follows those. So these two waterfalls have different orientations. This one is oblique to the stream orientation, makes it look like the water's coming straight out of the house. And part of the charm of the iconic view is those two orientations are different. The sandstone here is more massive and thick bedded. I think maybe that's why it has a different fracture set. This one's more bedded, even though it sits in a fluvial channel. So there could be a geologic explanation for why the two waterfalls have different orientations here. And I mentioned the 53-degree orientation of the house fits in the tectonic grain of the landscape that's reflected in the Bear Run, and it's within Wright's preferred orientation for organic design of this period. So our last example now is going to be Kentuck Knob. And I mentioned the Hagens had been to Taliesin. See the golden brown sandstone? It's Pennsylvanian sandstone, not dolomitic this time. There are pavers that have a different geologic origin, and we'll talk about those too. See that there are stickouts? Here's a preliminary map. This is a contour map Wright was given to work with at his studio. And I planned this at his ideal 60 degrees. This is a long terrace wall that's parallel to the living room here, 60 degrees. As built, turns out 70. And I haven't read how that happened. I know that there were some inaccuracies in the map. So I looked at, well, I wonder what the magnetic declination was in 1950s, 5 degrees. And guess what happens if you correct it the wrong way? 10 degrees. And that's 10 degrees. So there's some conjecture on how possibly that might have happened. But it's still within the range Wright preferred. There weren't trees at Kentuck Knob originally. There are a lot of trees planted there now. But they would have had a view like this. Looking to the east, there's Laurel Ridge, Laurel Hill anticline with Youghiogheny Gorge cut through it. There's the interior as it was originally furnished. There's carpet here over a stone floor that is exposed now. There's radiant heat underneath, so it's kind of nice and toasty that way. See the stickouts in the golden brown stone? Some stones have mineralized fractures shown on display. There's that window I mentioned that doesn't even look like there's a window there. It brings nature into the house. There's that long wall I mentioned, a terrace outside the living room. These pavers, like the ones on the front steps you saw, those came from M&S stone quarries near Grantsville, Maryland. And the current owner there and I hope to figure out which of their quarries these came from and which formation they are. They're fine-grained sandstones, lots of parting lineation, some nice current ripple marks, and a few vertical burrows, but we don't know what formation yet those came from. Notice the skylights with sunbeams and shadows, another organic design feature. This is the prow. That's that 60-degree azimuth wall. See the stickouts? It's a pretty massive sandstone. There's not a lot of sedimentary structures in it. I would guess probably fluvial, maybe distributary mouth bar type of environment. I'll mention that unfortunately there was a fire in the carport, so some of the stone's been replaced around the carport and the part of the house next to it. And there is lamination in that, but the color matches pretty well. And see how these boulders are built into it too, part of the organic design. Well, the current Kentuck Knob folks kind of forgot where this wallstone came from. And I decided to try to help them. So Bernadine Hagen wrote a really nice book. I have a copy, I'll pull it out later, about Kentuck Knob. It's kind of a rare book. It was never reprinted. But here she is sitting on stones that were split from boulders. So there was never quarried. There were boulders sitting on the landscape on another property they owned, not Kentuck Knob property, but another property they owned. They drove past it with a Wright intern, got out, intern had a hammer. It was gray on the outside, pretty nondescript. But when they hammered it, they found this golden brown color, which you now saw at Taliesin, that they all would have seen, and they said, that's our stone. So there's Kentuck Knob wallstone that comes from this property on the table there as well. So she gave enough clues that when I went to Uniontown, the Fayette County Recorder of Deeds and the tax assessor's office with maps and went back and forth, I came away 100% convinced I know what property this stone came from. And I was able to visit it with the owner, and he knew the wall stone came from there because the junior of the Masons was still living when he bought the property. And the Mason came over one day and said, you know, this is where the Kentuck Knob wall stone came from. And the property owner took me to piles of split stone. See how those are the same size and shape as the ones in Bernadine's book, except they're in the woods and covered with moss now. Well, Jim has a really nice geologic map of the Kentuck Knob area. There's Kentuck Knob itself, the house itself, not exactly on the crest, just a little below the crest, another organic feature. But it sits on Glenshaw Formation. And I'll show you that the split stone comes from the area of Green, the Alleghany Formation. Now I'm going to show you a cross section, but I don't show you where the cross section is on this because we're putting this on the internet. It's private property, and I want to respect the landowner's privacy. So I'll show you a cross section that goes through Kentuck Knob, Glenshaw Formation here. The topography came from P.A. Geode and the geology from Jim's geologic map. And those are those piles of split stone. You saw a picture of one of those. This is an area of boulders. So it looks like the stone came from the upper Alleghany Formation, maybe a little bit from the lower part of the Glenshaw as well. So those are the slides I'd hope to show you. I'm not sure how we did on time, but I hope we have a little time.
You did great, yeah. Thank you. Question, you showed us that prow, and the first thing I wondered was how did they drain those big rock walls so they didn't heave?
Yeah, that's a really good question, and I neglected to mention that it's stone veneer.
Oh, okay.
So some walls at Kentuck Knob are pure stone walls. All the walls at Fallingwater are pure stone walls. They don't have a concrete core. But in this case, this part of Kentuck Knob, there's a concrete veneer behind that, or a concrete behind that, and it's a stone veneer. And that varied with different structures.
Yeah.
One of the most beautiful houses, I think, in this genre is the Walker House in California, overlooking the Pacific Ocean and strand of sand at Carmel. And it's a Monterey Formation, which probably wouldn't be a great building stone. And it's, it's a veneer. So some of them are veneers. That's a really good observant question. Well, I invite you to come see the stone here from these buildings that we've talked about. I didn't have time to talk about Lynn Hall in Port Allegheny that was built by Walter Hall, the builder of Fallingwater, but we can talk about that too.
Tom?
Is this house, it's open for tours too?
Yes. Kentuck Knob is privately owned. It's a British ownership, but they're open for tours through most, if not all, year. Yeah. And I've gone on, a few tours there. They do a nice job. And it's a Grand Usonian house. It has a kind of living room with higher ceilings than usual for Frank Lloyd Wright houses. And a lot of people think it's a quite livable house in many ways.
It's interesting. It's a lesser known of one of his houses. Like Fallingwater, because Fallingwater.
Yeah, well, it's not far away, and you can see both. A little side note, Wright got permission from Kaufman to use Fallingwater sandstone to build Kentuck Knob. But when they thought about it more deeply, it would have been a bit of expense and a trip. It would have been wear and tear on the Kaufman's property at Fallingwater, and they decided to go with this other golden brown sandstone on their own property just a few miles away by road.
You mentioned one house had radiant heat. How were the other ones? Because I look at these places and think, yeah, heat bill here.
Yeah.
Big windows and.
I mean, I know the ones I've studied, which isn't very many so far, and Fallingwater doesn't have that, but that was kind of early in this organic design phase. It has radiators, and he would he would build in nice woodwork typically around those, so you can't even tell they're there.
Okay.
So some of them have radiant heat, and Kentuck Knob is one of them.
And all those fireplaces, right?
Yeah, and the fireplaces too. But the radiant heat, remember, that was really late in his career in life. It was built in the 50s, and he passed in 59.
So give a little preview, GSA meeting's coming up next
Oh,
month,
right.
and you're running a pre-conference field trip. What's that about?
Yeah, I should have mentioned that. So there's a sold-out trip to Graycliff from GSA Erie, but that also means there's a brand new geology guide, the first ever for Graycliff House. So that'll be in GSA Field Guide 71. It'll be a chapter in there. And I'm going to give a talk about Graycliff geology, but I'm also going to give a talk about those pop-ups together with Bob Jacoby and some of the things about variable orientation that I mentioned. I'm going to talk about that too. And for you in Pennsylvania, I know of one thrust fault on the lakeshore, just barely into Pennsylvania. It's in the 1998 Field Conference Guidebook. But I don't know of others in the Devonian shale bedrock beyond that. And my hypothesis is, you know how the Whittlesby and Warren shorelines rise in New York because there's more isostatic rebound after the glaciers retreated from the proglacial lakes that they dammed. And I think that the till and proglacial sediment's gone along the lakeshore in New York, and these pop-ups are there. And in Pennsylvania, you know, there's 30, 60 feet typically of till and proglacial sediment, sometimes 90 feet if there's a beach on top at the lakeshore. So I think those are held down, and I don't think there are pop-ups there. But there are a lot of pop-ups in the streams, right? When a stream gets excavated, there are a lot of compressional structures, and I suspect a lot of those are pop-ups. And you know, pop-ups happen in quarries, in glaciated and non-glaciated areas. They happened when they dug the Erie Canal. You know, they got pop-ups there too. So these are a feature that happens, and it was a pleasure to learn about them. I never knew anything about them before seeing those ones on the lakeshore.
We recently published a map near Erie. I'm looking at you.
Yeah. Well, which one? There was the
one
Jeff Greida?
Jeff Greida's book. And I think it was a long time since I looked at that publication, but he had pop-ups. I'm pretty sure that.
Yeah, I'd love to see that. There's a field trip after the Erie meeting by Lang to see small thrust faults and folds in creeks in Pennsylvania. He did a trip like that after GSA annual meeting, and there's a guidebook for that. And he's has like a variety of explanations. And you know that one of your own folks in the past wrote about the cross lineament that comes through there, and that there could be horsetail, you know, complex structures. And that's one possibility. But another possibility is these streams, their reaches have different orientations. And when you think about the state of the stress, unburdening, you know, the rock, taking and sizing the stream, and the stream changing orientation, that's an easy way to get different orientations. And those, they're typically not as well exposed as the one I showed you, where you can see the bottom of it. You only see a little fault and a fold, and you really can't see very much laterally in the bottom. I'm going to go on that field trip after the GSA. I'm looking forward to seeing those. When Lang wrote his guide after the GSA meeting in Pittsburgh for those, he said that he thought quaternary sediment was deformed by those. And that's hard for some people to accept that could happen. But I'm kind of seeing that could happen in places.
When those pop-ups occurred during quarrying and canal building and so forth, just out of curiosity, did they occur suddenly?
Yes,
or
with a pop.
with a pop?
Does anybody know Carl Brett? So I talked about one of these structures along the lakeshore when he had students out months ago. And he said he was in a quarry with somebody, and there was a pop up right under their vehicle, and it really was scary. There's one in the upper Midwest, Minnesota or someplace. They took away a really big tree, and in town they heard this sound. And when they went back to the woods, there was this little ridge with an irregular crack down the center. There was a pop-up there. And in some quarries, they have to close the quarry because of this. Another thing that helped me get my mind around this, it's well known that in some quarries where they're cutting dimension stone, it has to be very precise dimensions. They'll let the stone sit for a while because it deforms, right? And then they'll cut it to shape. So these things are real, and pop-ups happen in quarries in non-glaciated areas as well. There's a really good example in Australia. And in that example, never glaciated, there's a block of stone that moved inches, and there's a a fault gouge that's about this thick underneath it. I mean, if I saw that, I'd think, well, that's tectonic. It was deeply buried. But with inches of movement, you get a whole lot of fault gouge. And I didn't talk about it at all, but I've seen horizontal fault gouge in these rocks on the lakeshore in New York too, with splays going off the top of it, and they interact with joints in really interesting ways. You know, which came first, the joint or the gouge? And both happen. So there's some really interesting small structural features. And the one I showed you, a real structural geologist who does modeling, I mean, the amount of shortening changes vertically. The whole nature of the fold changes vertically, and you could model that. You know, you could model how much shortening and what that means for the rock and the stresses. Yeah, they're neat features.
Trying to get him to write an article for PA Geology.
Oh, yeah.
This is really cool stuff. So, hey, thanks a lot. Really enjoyed it.